Hello there, my name is Dominic Sheldon. I'm a senior consultant in the Climate Action Planning and Transparency team at Ricardo Energy and Environment, and today we are going to be going through a basic LEAP transport modelling exercise. And this session is being hosted by GIZ, the Advancing Transport Climate Strategies, or TRACS programme. This is not an official training exercise delivered by the owner and developer of the LEAP model, that's the Stockholm Environment Institute, or SEI. This is rather an independent session delivered by Ricardo Energy and Environment through GIZ. And we're hoping that today this will be a useful introduction to the software and should start you on your journey to becoming proficient in the LEAP software. So first of all, we want to just flag that there are other places to find more information about GIZ tracks and also using LEAP to model GHG emissions in the transport sector specifically. Ricardo Energy and Environment through tracks developed an assessment of mitigation potentials in Uganda's transport sector, and the full report of this exercise is available on the Changing Transport on the TRACS website, and that link can be found in the description of this video. That document goes through a lot of the basic principles we'll be going over today, so is a useful reference to have if you're unfamiliar with any of these and want to get to know them in a bit more detail. Next, we want to just give a brief introduction to the LEAP model itself. So LEAP stands for the Low Emissions Analysis Platform. As I said previously, it was developed by SEI, the Stockholm Environment Institute, and it is an integrated scenario-based modelling tool that can be used to track energy consumption, production, and resource extraction in all sectors of an economy. The benefits of using LEAP in a project are that it's familiar to many stakeholders. It's very commonly used around the world. This is because it's relatively simple to use. It's free for developing countries. It has low initial data requirements, so it's well suited to a country where accessing robust data has been or will continue to be and will be continue to be a challenge. But it is also very scalable. So even though you can build a very basic model, if you have those low initial data availability situations, as your data availability improves, you can scale the complexity of the model to reflect the availability of that data. So it's a very, very flexible platform. Finally, it presents the outputs of the model in a transparent and intuitive way, which is valuable when communicating the results to stakeholders. As I said previously, this is not an official training exercise delivered by SEI or through the LEAP team. And if you want any more information about LEAP, go to the LEAP website where there are a whole host of resources available and specific training materials in order for you to explore LEAP and become more proficient with it. These include specific training exercises where you can follow along step by step with an exercise with a PDF document that takes you through each and every stage of the process of building a model, and then also follow along a YouTube video where a demonstrator takes you through this exercise so you can compare the results that you're seeing on screen with their results, track through however you want, go backwards and forwards in time in order to make sure that you're comfortable with the outputs you're seeing, and it's a really great resource in order for you to increase your modeling proficiency in the LEAP platform. Also, there is a very extensive user guide available on the LEAP website. It has an overview of everything you might need to know as you're exploring the platform, and it's a really, really good resource to have open to you once you're learning the tool. Use it however you want. If you want to learn more about how the interface works, how scenarios are built, what are the functions that you might want to use, all of that information is in there. It's very easy to use, and it's a great resource to have to hand as you're starting to develop a model. Okay, so the next step we're going to go through is how you calculate GHG emissions. This will be a very high level, brief overview. So if you want any more information of this, please go to that document that we explained previously, which was the report that covered the Uganda mitigation potential exercise. This goes into the methodology in depth, explains from first principles how you calculate GHG emissions, how you do this historically and into the future. It goes through the whole process with references for you to explore. But for the purposes of this session, we are going to go through this quite quickly. So the basic principle of calculating GHG emissions is that there are three components. You have activity, an emissions factor, and then finally some GHG emissions. Essentially, the activity and the emissions factor are the inputs, and then the GHG emissions are your outputs. In the transport sector, the activity is the travel taking place. This can be in the form of the distance a person travels in a vehicle. The emissions factor is the CO2 emitted when fuel or electricity is consumed for that travel to take place. So this might be in the form of a kilogram of CO2 produced per litre of fuel consumed in order for that trip to take place. And finally, when you put those two together, you get GHG emissions that result from that activity. And this is often given in megatons of CO2 equivalent. So that is the basic principle of how you calculate GHG emissions. How do you then calculate those emissions in the future or for the future? There are 3 steps of developing a model that projects GHG emissions into the future. The first is to model those historic emissions. So that follows the basic calculation we just explained, but you're doing this for a historic period using existing activity data that you have to hand, much as you would when you're calculating a GHG emissions inventory. The idea being is to build a reference period for you to compare your future emissions against, so that you can see whether any trends that you see in future emissions match any trends that you saw in historic emissions. It's an important validation step for you to understand whether or not your future emissions look reasonable relative to your historic emissions. So this is the first step. You follow that calculation to calculate your historic emissions. You then develop the first of a set of scenarios. This is called a baseline scenario. And what this is saying is that what happens to those historic emissions if we don't change anything, or if we don't do anything further than what we've already got planned that is going to take place. And so this says that's our baseline scenario. That's what's going to happen without any significant additional intervention. And that gives you, again, another reference. Here's where we might be in 2030, 2040, 2050, 2100, for instance. Against this baseline, you can then model mitigation scenarios. So that's the methodology we're going to be discussing in this instance, is calculating emissions reductions against a baseline. So in 2030, under the baseline, emissions will be at a certain point. If you implement a certain set of measures, what are those emissions in 2030 under that mitigation scenario? And so that's what the methodology is that we're going to be exploring in this exercise. So as you implement measures, you're developing mitigation scenarios, and you can see what would happen to your emissions relative to your baseline if those measures were implemented. We're now just going to go through a very quick overview of the way that the LEAP model works, or the LEAP software works. This is a very brief overview. We're going to go through an active exercise in a short period. So don't worry if you think this is moving too quickly. So first of all, the LEAP model is structured by a tree and branches. So for the transport sector, that's a demand sector. It involves the consumption of a fuel, the demand of a fuel, for instance, and it can be broken down into 2 transport types: the transport of passengers and the transport of freight. This can then be broken down again into different modes. So these passengers might be transported on the road, in the air, by rail, or by water. And you have 4 different types of transport there, or modes of transport that you might use. Each of those are then broken down again into different vehicle types and different modes again. So those passengers traveling on the road might travel on a motorcycle, they might travel in a car, they might travel in a bus. And this is the basic structure through which you can structure your model. And after that, you can then associate a fuel with that structure. So you can say that for those cars traveling, they will use, for the majority of the time at this stage, petrol or diesel in order to travel. And so now you've got a whole picture of what energy consumption looks like within your model in LEAP. And here's just a brief screenshot of what that actually looks like in the LEAP software. And you can see that exact same structure taking place. So you have all the way from demand through your 2 different transport types, passenger and freight, your different modes, road, aviation, rail, and waterborne. You then have your different vehicle types again. So non-motorized transport, motorcycles, cars, small buses, and medium to large buses. And then you have different fuel types. And in the screenshot, you can see a few more fuel types, but the principle is the same. This is the basic structure that you want to get to understand in order to make the most of the LEAP model. Next, we're going to go through some key points of the methodology used when modeling transport emissions at a high level, just to ensure that when we go through the exercise, we'll have a common understanding of some of the terminology I'll be using and some of the methods that I will be employing. So first of all, terminology that you might hear me use will be the distinction between a top-down or a bottom-up methodology. This is terminology you might be familiar with, and it's a very, very simple distinction. Essentially, a top-down methodology takes an aggregated value. So we've got that calculation that we've seen on screen previously of that activity and that emissions factor multiplied together to get your emissions. A top-down methodology says that activity we can express in the unit of total fuel consumed, total energy consumption. So this gives us no information about how that fuel is consumed, how that energy consumed. It just says total energy consumed is our activity. We can then multiply that by an emissions factor to get GHG emissions. This is calculating emissions from the top down, rather than disaggregating your activity specifically by the way in which energy is consumed. It is just saying total fuel consumed, total energy consumed. This is in comparison to a bottom-up methodology where you're breaking down that activity into how that fuel, how that energy is consumed. How far did the vehicle travel? What was in the vehicle when it was traveling? How many people? How much freight was being transported? What was the energy intensity of the travel that took place? How much fuel was being consumed per kilometer traveled by that vehicle? And that is then all multiplied together to get your all multiplied together by your and also by your emissions factor to get your GHG emissions at the end of it. So essentially, you've disaggregated that total fuel consumed, that total energy consumed, and you've tried to understand how that fuel is consumed in order to understand better what your levers might be if you're trying to pull them to try and reduce those total emissions at the end of that calculation. You have a better understanding of where those emissions are coming from, which gives you puts you in a better position in order to then implement measures or experiment with measures that might reduce those emissions overall. And the way in which you might reduce these emissions would be through mitigation measures. And within the transport sector, there's a commonly used framework. This is called the ASIF framework, or ASI, alternatively. ASIF is an acronym, and it stands for Avoid, Shift, Improve, and Fuel. ASI is just the first three, avoid, shift, and improve, because fuel can be included in the others. But what this says is that there are 4 ways that we can reduce emissions from transport. First of all, you can avoid a journey entirely. So this is the effect of this is that you have a total reduction in vehicle kilometers traveled. You perhaps worked from home rather than traveling into the office. The journey was avoided. The second way is to shift. So you could move a journey from one mode to another, perhaps from a private car onto a bus. So there's a shift of VKM. That vehicle kilometers, the total vehicle kilometers doesn't go down. Instead, there's a shift in it. Some vehicle kilometers will move from one category, from cars, to another category, for instance, buses. There's then improve. So this is saying improving the energy intensity of travel, the fuel economy, for instance. And this is saying for each vehicle kilometer traveled, perhaps we consume less fuel as we go, increasing the fuel economy of a vehicle, for instance. Finally, you have fuel, which is the one that's less commonly used. And so this is reducing the actual carbon contents of the fuel that are consumed. So this is quite a sophisticated measure, which requires you have a significant amount of control over the fuel you are consuming. And this is why it's not necessarily often considered independently, because it's something that is not a low-hanging fruit when it comes to developing mitigation measures in the transport sector. And so a couple of examples of measures you might implement might be for your improve, you might have a fuel efficiency measure. So this is saying it's leading to a change in your energy intensity. That's the effect you're looking into. So you're consuming less fuel for the distance you're traveling. Might also have a freight modal shift measure. So this is that shift point of ASI or ASIF, as we discussed before. And this is moving VKM between categories. And for instance, this might be shifting freight from road to rail. And this is important because these two measures are measures that we will model in the future exercise that we are going to go through in just a few minutes. Okay, so finally, we're just going to go through a brief overview of the LEAP model, just in presentation format. So this is just to get some basic familiarity with the tool, so that when we open the tool to do the exercise, it's not the first time we're seeing some of these elements, so it's going to be a little bit easier to become familiar and to start using them. So to start off with, when you open a new LEAP area, which is what it's called in LEAP, when you start a new model, you have to set up some settings, some basic parameters around which the model will be structured. One of these are the years across which the modeling period will be. So the first of these is the base year. So this is the very first year that will be in your modeling period, the very first year of the historical period. So as you see on this, in this case on screen, 2010 is the first year of the historical period. Then the next number is the first scenario year. So this is the first year projected into the future. So in the example on screen, 2011 is that first year. So that means there's one historical year, that's 2010, and then the first projected year is 2011. Finally, the third value there is the end year. And so that's on the screen, that's 2040. So that's saying that the projected period runs from the year 2011 all the way to the year 2040. And so a way to look at this is the graph on the right hand side of the screen here. So you'll see the historic period. And so we've got a slightly different set of inputs on the left hand side here. So where we've got the first year, the base year being 2003. We've got the first scenario year being 2020. So you've got a much broader historical period there, as you can see. And then you've got the end year being 2050. So you've got an even broader projected period as well. And across those three values, you get the total modeled period. Next, you've got the interface, the basic interface of the LEAP model. And as you can see here, there's a lot of different inputs. You can see a lot of different elements that can be varied. And so it's just an element. It's just a case of starting to become familiar with this because it's actually a very simple interface. It just takes some getting used to. So the first thing to do when thinking about this is to break it down into a set of components. First of all, we're going to start with the branches. We're already familiar with this from the explanation earlier in the session, where we developed a tree structure across which we added branches to develop the structure of the model that we're going to be developing. So what we can see is this on the left-hand side of the screen. We can see that tree structure in folder format. That's just the icon that LEAP uses to demonstrate each branch of that tree. Next, moving over to the right, you've got a variables element. So here is where you're going to start to input your data and vary the variables that you're trying to model. And the most critical point of this are the expressions, which is another part of this. So that big white bar you'll see across the middle of the screen, think of that as like your formula bar in Excel. That is where you're going to enter your data. There's also where you're going to enter any functions that you want to use to manipulate that data. And it's where you are going to also enter any calculations that will project some of that data into the future. That's where your inputs are going to go. Next to those, you've also got what are called the scale and the units. So the units are obviously critical because, for example, you might be modeling vehicle kilometers, you might be modeling the gigajoules of energy per vehicle kilometer, etc. So the units of the data you're modeling is really critical. So you must select those, and you can also select a scale. So whilst you might have vehicle kilometers, you might have several million vehicle kilometers or several billion vehicle kilometers. And so you can select million vehicle kilometers, for instance, or billion vehicle kilometers, which means the data that you're inputting is more simple. It's much easier to put 1 million vehicle kilometers than 1 million vehicle kilometers, if you see what I mean. It means that it's much easier to quality assure when you're checking that, rather than saying, is that enough digits? Have I got all of the 7 digits I need in order to be in the million range? Instead, you can just QA a smaller number. Finally, you've got the information box in the bottom right-hand corner. So this is where you can see a visualization of any data you've inputted. For instance, here we've just got a basic bar chart that's showing the percentage share of the road mode of your activity level, and it's saying 100% of the activity level is in road in this instance. And so this is where you also might see a table of that data. You can get you can have a bit more space to build your expression in there. You can add notes, etc. You can also find some help here. So that's where you're going to see whatever data you put into that expression bar at the top. That's where you're going to see it visualized. Okay, so to take a step back towards those branches again. So as I said, you've got that bar on the left-hand side, which are your branches. And the way in which this works is we have a structure in our minds that we can see in the bottom right-hand side there. We know that's the structure we want to build in our model. The next challenge is how you actually do it. So as I said, LEAP uses these folders as the icon to represent each branch. So what you do is you think of under each branch, you will right click it and you'll get an option to add something. And as you can see on screen here, it says add branch under, and then whichever the branches you clicked, in this case, I've clicked on demand. So I'm right clicked on demand. It says add a branch under demand. And here I can start to add transport, for instance. Under that, I could add passenger. Under that, I could add road. Under that, I could add cars, for instance. So you can start to see the interface with which you start to build up one of these models. But don't worry about this. We'll go through this in the exercise itself, but this is just to get an idea of the way in which you interact with the software and the way in which you start to build a model. Okay, the next point are expressions. So as I said, your expressions are the main way that which you interact with the model in terms of the data you input. And so as you can see on screen, we've got a breakdown of information here, exactly as we were just describing, but just in a bit more detail this time. So we've got our branches on the far left-hand side. As you can see here, in this case, we're looking at the passenger transport sector or subsector rather than freight. And then we're looking at two modes. We're looking at road and we're looking at rail. And the expression here, we've got two types of data input. On that passenger row, we've got 1,000 passenger kilometers. And then we've got a set of data input there. Don't worry about the exact formula as it stands. That's something we can go into. But at the moment, you can see that there are 1,000 passenger kilometers being inputted into that level. Then underneath that, in the branch underneath that, you have road and you have rail, and we have a different type of data here being inputted here. Here it's percentage share of that passenger kilometers. So here's where you can start to see that cascading structure, that branch structure interact, and you can see the way in which the data you input is dictated by the structure you've created. So for that passenger level, we've entered passenger kilometers. And now we're going to say, okay, of those passenger kilometers, what percentage are traveled by road and what percentage are traveled by rail? And then we have a certain function here that we've used in order to input that data. And here we have an expression that's showing a change over time, which is something we'll explore when we go through the exercise itself. But that's just a very brief explanation of the kind of expressions you can use to input into LEAP. Here is an overview of some of the expressions you might use. We won't go into these in detail. All of this information is available on the LEAP website if you want to review this in more depth. But the idea being is you can put anything in from a value. You can put in pi here, 3.1415, or you can put in a specific function that will manipulate the data for you automatically. So you can do a basic formula. You might want to just do a basic multiplication, addition, subtraction, division, or you might want to say, well, actually, I want the value I've inputted to grow by 3.2% every year. So there is a growth function. You can use that. You can tell LEAP the growth rate that you want to use, and then LEAP does the rest of it for you. You also might want to do an interpolation. And I'll just cover these two and then one more before moving on, because I don't want to get into these in too much depth. But an interpolation is where you say a year and a value, and then another year and another value, and then LEAP draws a straight line between them for you. So it's a great way of, if you have some data that isn't complete, say you only have 10 out of a 30-year period, LEAP will draw a straight line in between those gaps to mean that you've got a rough estimation, a good interpolation of what that data might be. Finally, the last function I want to talk about is the remainder function. This is really useful. So because it's the way in which LEAP is structured, you want to be changing these inputs to model the different effects of your measures. If you're modeling a percentage share, as we were just describing, where you had the percentage share of passenger kilometers, what you might want to do is you might want to say, okay, well, 70% of that share is road, for instance. 70% of those passenger kilometers are road. And then obviously, if you have only two variables, then the remaining 30% will go to that second variable. So it would be rail. So you'd have 70% for road and 30% for rail. So what you could do is you could hard code this. You could write 70 for road and you could write 30 for rail. Alternatively, you can use a function known as remainder. And so what you do is you set the limit. You say my total is going to be 100. So you say remainder 100, and then you've already told LEAP that 70 is going to be your value for road, and it says, great, 100 minus 70 gives me 30. And the value of that is that if you then change that value for road, change that 70, you say, maybe you use an interpolate function, and you say, but in 10 years, it's going to be 60, and in 10 years after that, it's going to be 50, then LEAP will automatically calculate the remainder for rail. So when it becomes 60, rail will become 40. When it becomes 50, rail will become 50. So it will do that automatically for you within the model, which means you only have to change one variable. It's just a way of simplifying your life, making it a little bit easier, and it's worth becoming familiar with. Fine. Well, another point to think about now is what we've talked about so far is essentially an energy demand model. We haven't really talked about emissions yet. So the way in which you add emissions into LEAP is through a function called multiple effects. As you can see on the left-hand side here, in the left-hand screenshot there, you've got your branch structure, you've got your tree structure, and don't worry about the terminology, multiple effects. It's just the terminology that LEAP use. Once you're familiar with it, it will seem very intuitive. It's just a different terminology than you might be familiar with. So you can see that branch structure. You can see passenger, road, cars, and then we're looking at the fuel of gasoline. And so we want to add an emissions factor for gasoline. So what you do is you right click on gasoline, you click on the option that says add multiple effects. You get a wizard that pops up with a whole bunch of different default emission factors already in LEAP in a database for us to select from. So for instance, in that central screenshot there, you can see that there is the IPCC tier 1 default emission factor for road transport for gasoline in there already. So what we can do is we can select that and then add that into LEAP. And so what that means is if we don't have country-specific emission factors, if we don't know exactly what the carbon content and the fuel that we use within the country, we can use the default emission factors, use those international standards, and it means we're still going to get a good value out of it that can be updated in the future, but it's at least something for us to start with, at least the baseline to start with, because otherwise we could spend a lot of time and effort trying to find a country-specific emissions factor, whereas actually we could have a good value, a relatively workable value from the defaults that we can go with and then refine that in the future. So all of this is built within LEAP, so it's a great way of us building a model quite quickly that we can then refine over time. Right, after that, we're now ready to build our model. So what we're going to do is we're now going to switch over to the LEAP software. And then we've also got a worksheet accompanying the model. And we want to work through that worksheet. And you can download that worksheet. If you click on the link in the description below, that should take you to the TRACS website, the Changing Transport website, where you should be able to download a copy of this exercise. And then you can follow along with the exercise, follow along with me, and we're just going to build a very basic transport model together live. And then hopefully that should put you in a good spot to then begin to take your LEAP journey further as you start to learn more about the software and what it can do. Okay, so now we can move on to building a model itself. So what we're going to do is we're going to follow through an exercise where we're going to develop a basic transport model. We're going to build the historic emissions. We're going to develop a baseline scenario, and then we're going to develop a mitigation scenario as well with a couple of measures in it. And so the way to do this is we're going to have the LEAP model open. That's one thing we need. We need to have a copy of LEAP open. And you can find guidance for getting a license, and you can go on the LEAP website in order to get more guidance on this as well. But once you have the LEAP model open, what you then want to do is also open the basic LEAP transport model exercise worksheet as well. So you should be able to find this in the description of the video below. There should be a link to the Changing Transport website where you should be able to download it. And the idea here is you can follow along with the video whilst having the exercise book open. The exercise book contains all the data you need. It contains some demonstrations of the kind of structures to use, the information, the way in which to build the model, and so that hopefully what I'm doing on screen will make a bit more sense to you if you're following along with the model, with the exercise booklet. And this is the same way that the exercises the Stockholm Environment Institute themselves put out. They have a sheet that you follow along with. It's a really effective way to learn because there's always a reference for you to work from if you need it. So what we're going to do is we're going to dive right in, and we're going to navigate to LEAP now to start the exercise. So here's the basic overview of LEAP. It's relatively straightforward, and the first step we are going to do is going to create a new area for us to work in. So this is very straightforward. You're just going to navigate to the top left-hand corner of the screen where it says New, and we're going to click New, and this is going to create a new area. Now, we want to name this area whatever we want, but we obviously want to name it something rational that makes sense. So we might call this LEAP Transport Exercise in this instance. I'm going to hit OK. It's going to say, do I want to save changes to the area I'm already in? No, that's fine because it's just a demonstration area. So what it's going to do is it's then going to create a new area for me to work in. So straight away, as soon as I've done this, it's going to give me a pop-up that says, we suggest you review the settings for this new area. This includes the scope of the analysis, its base year, end year, and default energy and currency units. Do you want to review these settings now? So the answer to this is yes, we do want to review the settings now. However, there's only one page of the settings that we want to review, and that's going to be the years, as I previously explained. So this is where we're going to set the years for the modeling period. So we're going to hit yes. It's going to open the settings, and we're going to go straight to the years tab at the top. You can see there's some other tabs. So you've got scope and scale, calculations, optimization, various other tabs. For a basic model like this, we don't need to be concerned with any of those. All of those defaults will be fine for what we're doing here. But what you'll see on screen are those same inputs that I previously demonstrated. You've got the three main inputs that we need to be concerned about here: the base year, the first scenario year, and the end year. So in the worksheet, you'll see that the base year is 2019. So we're going to go ahead and type that in here. So that is saying that the very first year of the historic period is going to be 2019. Then we can input the first scenario year. So this is saying the first year from which we're going to start projecting into the future. So for this model, we're only going to have one historic year, 2019. So the first scenario year is going to be 2020. So let's assume that maybe we've done one GHG inventory. That was for the year 2019. So that's the only year for which we have historic data. So we're only going to have one historic year as we input that into the model. And therefore, the first scenario year will be the following year, 2020, and we'll project into the future. As obviously 2020 is in the past, but it's all about what is relative to the data we have. So based on the data we have, 2020 is the first scenario year. Then we're going to set the end year. So this is the final year of our calculation period, and this is going to be 2050. We're going to model all the way out to 2050. And so once you've made those three inputs, and those will be in the worksheet as well, you should be able to see those, we're going to hit close. And then there's going to be a tiny processing period in which LEAP is now established that any data you input is going to be across that modeling time period. Okay, now the next stage, step 1.3 in your exercise booklet, is going to be building the branches of the tree structure. And I'll give you an example of what the tree structure is going to look like there. So as I mentioned previously, we're going to start with demand, because we're consuming fuel, consuming electricity, depending on how we're fueling. But we are consuming a service, and therefore it's a demand side function that we are going to model. So we're going to right click demand, and we're going to go to add. That's at the very top of that drop down, and there's a little green cross. So you hit add, and a pop-up appears, and this says that do you want to add a branch under demand? And the answer is yes. So what we want to do is we want to add a category. That's correct. That's what the input we want to do at this stage. None of these other inputs are what we need at this stage. So we're going to select category as the default, and then we're going to say transport. This is because we might model other demand categories. So this is just going to say that this is the category that we're going to model. We're going to model transport. It's the only category we're going to model now, but it's good practice to understand that this is how you would set out your model. Next, we're going to add another branch. That is going to be the next branch underneath transport, which is going to be passenger. So these are the types of transport that we are going to be modeling. So to reflect that, we also need to add freight. So now under transport, as you can see, we've now got to make this slightly larger as well, so hopefully it's even clearer. You can now see under transport, we've got passenger and we've got freight, those two types of transport. Now under these, we want to start adding some of our modes. So go to passenger, we're going to hit road, we're going to hit add, and we are going to add another category, and that category under passenger is going to be road. So what we're saying is that the one mode within passenger that we're going to model is going to be the road. Under freight, we're going to hit freight and add a branch under freight. We're also going to model road. But then also under freight, we're going to model rail. So now you can start to see this basic structure taking form. So we have transport, we have passenger and freight, and then we have road under passenger, and we have road and rail under freight. Now we can start to add vehicle types. So under road for passenger, we can right click road, add. We're going to add a category under road, and that road is going to be car. And in this instance, we're just going to model that one vehicle type under road. Then we're going to go to freight, going to right click road, and we are going to add a category. This category is going to be LDV, or light duty vehicle. So think of this as a small van or a small truck. We're going to right click road again, and we're going to add another vehicle type. In this case, it's going to be HDV, heavy duty vehicle. So these are just a couple of examples of the way in which you might disaggregate road, just so to demonstrate how you might do this. Now, for rail, we don't need to add another branch because we don't need to specify the vehicle type at this point. We're just going to assume that any rail vehicle is going to be assumed to be the same. You could disaggregate. You could have electric locomotives. You could have diesel locomotives, steam locomotives, etc. But in this case, we're just going to stipulate rail generally. We're just going to assume to aggregate all of those vehicles as one. So that is step 1.3. That's complete. We have our branch structure now. So what we're now going to do is move on to step 1.4, which is where we're going to select the methodology for how we are going to model each of these vehicle types under each of these modes. So what this means is previously we talked about a top-down methodology or a bottom-up methodology, and we talked about how the way in which to decide this is based upon the measures that you might want to model. For instance, if you want to model a measure where there's modal shift, so you have vehicle kilometers moving from one mode to another, you would want to have vehicle kilometers as a data input in your model already. So if you do a top-down methodology using energy consumption as your activity, you're not going to have vehicle kilometers as your data input. So you won't be able to model that measure in the same way. You might be able to use a proxy, a proportional change, for instance, in order to model it. But the most effective way to do that would be if you developed that subsector, develop that mode from the bottom up, inputting that activity data of how far the vehicles have traveled and the proportion of that distance traveled between different modes. That might be a lot of information, but don't worry, we're going to go through this step by step. But it's really, really important that that's understood. So in this case, we're going to model two measures. We're going to model a freight modal shift. So that is saying we're going to move freight from the road to the rail. And then we're also going to do a vehicle fuel efficiency, vehicle fuel economy measure. So we're going to improve the fuel economy of vehicles on the road in the passenger sector as well. So those are the two measures we need. So obviously for those, we need to think about the effects. So for that freight modal shift, we need to have vehicle kilometers in order to model moving vehicle kilometers from the road to rail. And for that vehicle fuel economy, vehicle fuel efficiency measure, we need to have the energy intensity, that fuel economy value, the amount of fuel that's consumed for every vehicle kilometer traveled. So therefore, we are going to have to use a bottom-up methodology for the passenger sector, for the road mode, in order to get that vehicle fuel economy. And then we are also going to have to use a bottom-up methodology for the road in the freight transport type, in order to model that shift from road to rail. So that's just something to start with. So now what we're going to do is we're going to start to input this data. So to set LEAP up in a way that it's able to be structured to accept bottom-up data. So we are going to right click our car here under passenger, under road, right click car. We're going to hit add again. So it's going to say add a branch under car. Do you want to add a category? We're not actually going to add a category this time. What we're going to do is that we're going to add a technology with an energy intensity. So there are two options here. There are several that appear in the drop down, but there are two options we need to be concerned with. There's two cog icons there, a silver or grey one and then a red one. And the silver or grey one says technology with energy intensity. This is a bottom-up methodology. And then it has technology with total energy. That is a top-down methodology. So as we just explained, we want to do a bottom-up methodology. So we are going to select the first cog, technology with energy intensity. Now, it's now another input has appeared, which is we are going to select the fuel that we are going to use. In this case, it's defaulted to electricity. So we are thinking about cars on the road for passengers. And so we are going to assume that all of these cars in this demonstration are going to be gasoline powered. So we select gasoline, it auto-populates the name as gasoline, and we hit OK. So now we have this technology added for the road sector in passenger. So this brings us to the next step. So now we want to add the same for the freight transport type. So we're going to right click on LDV, on light duty vehicle. And now we're going to assume that instead of, we're going to select technology with energy intensity. And now we're going to assume, rather than gasoline, we're going to assume diesel. So we're going to select diesel from the list, auto populates the name, and we select that. Going to do the same for HDV, for heavy duty vehicle. Add a branch under HDV, go to technology with energy intensity. It's a bottom up methodology. We are going to select diesel again. Now we're starting to see a bit of a structure developing. So for all of the road vehicles we now have a technology with an energy intensity. This brings us to the next step, which is to add the same for rail. So we do it in the same way, even though the branch is slightly different. We right click rail, click add. It says add a branch under rail. We go yes, technology with energy intensity. In this case, we're going to assume that it's all diesel powered. So this is just saying we're going to use the fuel of diesel. So it has the chemical composition of these fuels built into it. So therefore it can understand the energy content, etc. So once you put in your vehicle kilometers traveled and the energy, the fuel that you used and the amount of that fuel you used, it knows how much energy is in that. So therefore it can calculate how much total energy you've consumed, and then you can build that basic energy demand model. So we're going to add diesel for rail. So now we've added all of our technologies for each of our modes. So it's excellent. We're in a really, really good spot now moving forward. So now what we need to do is to get the model ready for our data input. So what this means is we are going to have to select the units. So the easiest way to do this is to go up to passenger, and we are going to input the units that we need for the activity data that we need. So as you can see in step 1.6, which is the step immediately after step 1.5, set units, you can see the types of activity data we need for each of these subcategories, and we can use this to determine the units we need to input. So for passenger, you can see that we want to input million vehicle kilometers, and actually it might even be we could step one level up to transport here, and so then we have passenger and freight together. And we can change both of these at the same time. It makes it even easier for us because the input is going to be the same. So we're going to go to the units on the far right hand side of the screen in the passenger row. We're going to click it, and a little 3 dots appears, a little ellipsis. And then once you click that, a wizard appears, a unit wizard. And so from here, we can select a unit. So what we're going to do is going to navigate to the transport section. We're going to expand the little plus sign there. And then we're going to select one of these units. So in this case, we know we want to use vehicle kilometers. So we're going to select vehicle kilometers, hit OK, and now the input has changed. It started as percent share. That's always going to be the default. Now we've changed that to vehicle kilometers. For that transport at the top, don't worry about that. We're not going to be using it, so we don't need to worry about it. We can, for instance, navigate to this and hit no data because we're not going to be inputting any data in that level, but it doesn't matter. It won't cause any incident if you're just leaving it blank also. But we know that for freight, we also want to do the same. So we'll go to the units, go to share, and then we'll go to transport and select vehicle kilometers. We're not using passenger kilometers or ton kilometers in this instance because we don't need to. We don't need to have that load factor included. That's for a greater level of sophistication in the model itself. However, as we talked about before, at the moment we have no scale of these units. So at the moment, the expression is that are 100 vehicle kilometers. And so if we wanted to write 1 million vehicle kilometers, we would have to write the number 1 million in this expression bar. And this leaves us open to errors. So we don't want to have to do that. So ideally, we are going to change the scale to million vehicle kilometers. So if you click in this scale box, a little drop down appears. So you can click this and then a bunch of scale options appear. One of these is million. So we're going to select that because we know from step 1.6 that million vehicle kilometers is going to be the data we want to input. So we've got, now it says 100 million vehicle kilometers, which sounds much more reasonable for a country level model. We're going to do the same for freight as well. We're going to input both of these. And so now we've inputted that both of them, both passenger and freight, have a total activity level of 100 million vehicle kilometers. And you can see at the bottom, LEAP has now done a calculation for us, and it says, okay, well, total transport vehicle kilometers traveled is 200 million. and therefore 50% of that is passenger, 50% of that is freight. So you're starting to see the way in which LEAP fills in some of these gaps. So now we're going to go to one level down. We're going to go to passenger. And what we're going to do here is we are going to start inputting some additional data. So because we have this 100 million vehicle kilometers for passenger, what we now want to do is one level below that and road, so the branch below that, we want to input the percentage share of that vehicle kilometers that are traveled by road. Now, we only have one branch underneath passenger, so therefore, obviously, 100% of those vehicle kilometers are going to be traveled on the road. So the 100% share of vehicle kilometers is here all correct. That's already fine for us. So what we can do is we can then go to freight instead. Now, we've got the same situation here, the same set of inputs. We have 100 million vehicle kilometers for freight, but now we have a contradiction. We have both road and rail stating that they own 100% share of vehicle kilometers. Obviously, that's an error. That leads to a total of 200%, which is impossible. So we need to input something here that's going to give us a more rational idea. So here we're going to assume, as you can see in the exercise, that 80% of our vehicle activity is going to be on the road. So we type in 80 in this expression bar here, and we hit tab, and now it changes. However, we've still got this inconsistency. We've got 80 and we've got rail having a 100% here. Now we're going to use our first function. We're going to type the word remainder and open brackets. Now a little wizard pops up that says that you're going to be using the function of remainder. We don't need this right now, so we're going to type it in ourselves. But what we're going to do is we are going to enter 100 in here. Sorry, once that wizard comes up, if you hit cancel rather than OK, it won't keep popping up. So type in remainder, open brackets, 100. So as I was explaining previously, this is saying the total we want to consider at this level is 100. So I want you to look across all of the other modes, see what they add up to, and then whatever's left, give rail that remainder. And so this is saying, well, road is 80%, so therefore the remainder will be 20%. So we hit tab, and now it's done the calculation for us. So now whatever we do to road, rail will adjust automatically. This is a really good, it's an automatic way of us doing this calculation without having to input it manually. Okay, there's one more input we're going to make now. So we're going to go down to road, and then we can see how for light duty vehicles and heavy duty vehicles underneath freight, we also have that same inconsistency of more than 100%. So now this isn't a data input we're going to use, but this is just for demonstration. What we're going to do is we are going to input 50% share of vehicle kilometers for LDV, and we are going to input a 50% share, or we could physically input a 50% share, or we're going to enter remainder 100, enter, and it will calculate that 50% for us. So this doesn't matter too much, but it's just a way of demonstrating the way in which we can break down a mode. So now all of our data inputs are there for the activity level. We can see that if we go to rail, it has 100% of total rail activity is using the fuel diesel, so we know that's correct. But all of our activity is accurate. So now we can move on to step 1.7. Step 1.7 is to input the energy intensity data for historic years. So as we explained, this is a bottom-up methodology where we're going to have an activity level, and then we're also going to have a energy intensity, or a fuel economy is another way of thinking about it. So we're going to go up to the technology, the gasoline. We're going to click that. It's going to open the input boxes on the right, and we're going to, rather than in activity level, which is where we've been, we're actually going to go to final energy intensity instead. And here we have a slightly different input. It's saying for the fuel gasoline, and the units are gigajoules per vehicle kilometers. This is saying it's the energy within that fuel, how much energy is consumed per vehicle kilometers. But we can change this. So generally, we might have this data in, for example, liters, and we might have the fuel economy value in liters per kilometers traveled, for instance. So we're going to change this. We're going to click on this box. It's going to open up a long list, and we are going to go all the way down to liters. We're going to hit tab. So then it's going to say LEAP is going to automatically give us a pop-up, and it says could not convert the expression 0 for unit liter. So what this is saying is that if you have a value in there already in that expression box and you change the units, LEAP will actually try and give you an automatic conversion if you have a value in there. So if I had 100 gigajoules in there already and I converted it to liters, LEAP would automatically convert that 100 gigajoules into the equivalent in liters. Very, very useful feature. We don't need it right now. So we're going to hit OK. Anyway, doesn't make a difference to this point. So now we know. Now we have liters as our unit. Now we're going to enter our first value. So in the sheet for step 1.7, you'll see that for petrol cars, we have a energy intensity of 0.12 liters per kilometer. So we'll enter this here and we have this value. So this is just for our historic year. All of this is just for our historic year of 2019. We're not looking at anything into the future just yet. So we've now entered 0.12. That is our fuel economy for petrol cars. We go to diesel, light duty vehicles in road. We can do the same. So we're going to change gigajoules to liters. We go down to liters. You can also type liters and the same thing, and you'll navigate to it immediately. Saying the same thing, we'd like to convert it. We don't want it to, so we're going to input the value, 0.13. We're then going to go to heavy duty vehicles. We're going to do the same. Input liter, don't want to convert it. You can always turn off that pop-up if you want. I'm going to put 0.29 in this case. And we're going to go to rail. And here we have a slightly different unit. So we're going to use this unit. So instead of gigajoules per vehicle kilometer, we're going to go to kilojoules. So this is a slightly, we just have, different data will come in different formats, and LEAP has the flexibility to use these. And now we're going to input a slightly different value. So it's going to be 214.8. Now we've got that energy intensity data in there as well. So now technically we have a full working energy demand model for the year 2019 in our example. So now in order to make this a greenhouse gas emissions model, we need to do the next step. And so that is going to be what's called adding multiple effects. So what we're going to do is we're going to right click on gasoline for road passenger cars, and we're going to navigate to where it says add multiple effects. We click that and a box appears with a large list, and it's already selected one. And so what this is LEAP has selected a default emissions factor from the Intergovernmental Panel on Climate Change, from the IPCC. These are all populated in a database already. It's already selected one. It knows we're in the transport sector. It knows we're in road. And it said, OK, how about gasoline as the tier 1 default emission factor of gasoline? How about that as a starting point? And we're going to go, actually, yes, we don't have a better option right now, so we're going to use that. So we hit OK. There's a slight amount of processing. You'll see there's a small arrow that's appeared next to gasoline. We click that, and now we have all of these gases that have appeared for gasoline. So all of these multiple effects. So greenhouse gas emissions, we've got nitrogen oxides here, nitrous oxide, various different gases that are being modeled. So what this means is that all of this is now available. All of these, what's called average environmental loading, as you'll see, there's a tab up here called average environmental loading. So all of this is now inputted into the model. So now what we need to do, we need to add the same for the other fuels. So we right-click diesel under road freight. The same thing. It says, OK, road. We think you're doing road, and we think you're doing diesel. How about the diesel tier 1 default emission factor? Yep, that sounds perfect. Same for heavy duty vehicles. Add multiple effects. Diesel tier 1 emission factor. Perfect. OK, but what about rail? That's not going to need the road default tier 1 emissions factor. We're going to need a different one. So we hit add multiple effects. Pops up. And unfortunately for tier 1, we have coal and we have oil. We don't have diesel. So what about under tier 2? So LEAP has several defaults that are inputted here. So we're going to have, so it has the IPCC default factors, and then it also has the factors available from an example country, in this case Argentina. So what we're going to do is we're going to click on the tier 2 default factors, and here we can see that there is actually a diesel engine default factor for European diesel engine railways. We're not too worried about how close they are to our exact fleet at this stage, and that's the decision you have to take when you model your specific system. So we're going to click European diesel engines railways under the tier 2 default emissions factors and click OK. Now we have all of our multiple effects built in. We now have all of the information we need to model the historic year 2019, the emissions of that year for our system. So what we now need to do is think about the future. What we're going to do is move on to modeling a baseline scenario. So we're going to move on to the next step, step 2.1. This is where we're going to start to create a baseline scenario. So actually, so far, as you can see in the top bar here, that says there's a little drop-down input that says scenario and it says current accounts. So this is just LEAP terminology, LEAP language for the historical period. So what we want to do is we want to add another scenario on top of this historical period. So there's a little button at the top here that says scenarios. We're going to click that and then a wizard appears. We are under current accounts currently. That's the only scenario we have. So what we want to do is we want to hit add, and it says add scenario under current accounts. And we go, absolutely. We would like to add a baseline scenario. We input baseline, and now underneath current accounts, we have baseline. So you can see that whatever is inputted into current accounts is inherited in the baseline scenario. We hit close. But currently, LEAP is still in the current accounts view. So that's looking at the historic emissions, looking backwards in time. We want to be looking forward in time into the future in our baseline scenario. So we're going to go to the top of the page where it says scenario, and there's a drop down that currently says current accounts. We click this and you can see that we have two options available to us, current accounts or baseline. That's the baseline scenario. So what we're going to do is we're going to click baseline. And LEAP's going to update and it's going to tell us, okay, we're now looking into the future, as we can see along the bottom of the page here. Now we've got a view from 2019, our historic year, all the way up to 2050. So this means we can start inputting assumptions into the baseline scenario about how our activity data is going to change over time. So what we're going to do is we're going to click on transport, and it's going to show us both the passenger and the freight activity. That's in million vehicle kilometers, as we inputted earlier. And what we're going to do here is we're going to input a very, very basic function. So we're going to click where that 100 is. So you can see that the 2019 value is populated there from the current accounts, from the historic emissions. And we are going to input a value into the expression bar for the future. So we're going to click where it says 100, and we're going to type the word growth, open brackets, and then LEAP's going to pop up a little growth rate wizard. That's what this is saying is we know you've used a function that's telling us that we want to input a growth rate. What is that growth rate? So we're going to input 10%. So every year that passenger million vehicle kilometers is going to grow by 10%. So we hit OK and tab, and you can see that growth rate is populated in the graph in the bottom of the screen. We're going to do the same for freight. So we're going to write growth, open brackets. A wizard's going to pop up. We're going to input 10% again, hit OK and tab, and you can now see that that assumption has also populated for the freight. So now we know that total freight kilometers and total passenger kilometers are both growing at the same rate across our projected period all the way up to 2050. So these are our baseline assumptions, very basic baseline assumptions, but this gives us a basis from which we can start to model emissions reduction measures. And so the way we do that is we do it in the same way as we built our baseline scenario. We go up to scenarios, click that, and now underneath baseline, we are going to add another scenario. Before we added a scenario underneath current accounts, whereas now we want all of our mitigation scenarios to be inherited from the baseline scenario. Those growth rates that we just inputted, we want those to be built into every scenario we build from here out. Those are the baseline assumptions. So we click on baseline and we hit add. Now the first scenario we want to make is a scenario which is going to model the effect of a fuel economy measure. So what we're going to do is we're going to name our scenario fuel econ. Yeah, okay. Now one of those scenarios is populated under the baseline. We're going to right click baseline again, and we're going to add a second scenario. This one is going to be called freight shift. So what we're doing here is we're going to model two measures. We're going to model a fuel economy measure. So that's underneath the intensity of the ASIF framework, the avoid shift intensity fuel. So it's the intensity, that emissions intensity, or the energy intensity even. And then we're going to also model a shift measure, and that is that freight shift. So moving those vehicle kilometers from one mode to another. So we're going to hit close, and that's going to tell LEAP to create these scenarios. So now when we go up to the scenario toggle at the top of the page, rather than just current accounts and baseline, we now also have freight shift and fuel econ. So we're going to click fuel econ to start with, because that's the measure we're going to model first. And then LEAP is going to change the view to showing that scenario. And now what we're going to do is build a very, very basic measure. So we are going to go to passenger, road, car, click car, and then navigate to final energy intensity. And as you can see here, we have our 2019 value of 0.12 litres per vehicle kilometre. And the measure we are going to implement is an improvement in the vehicle fuel economy. So the improvement means that it consumes less fuel, less litres of fuel per vehicle kilometre. So what we want to do is we want to reduce this value over time. And we're just going to use some basic assumptions here for the sake of this exercise. But this is just a way of modeling this kind of effect. And you could do something similar if you had some more specific assumptions. But the assumptions we're going to input are that in 2030, there's going to be a 10% improvement. In 2040, there's going to be a 20% improvement. And in 2050, there's going to be a 30% improvement. And the way we model this is by doing a very basic sum. So we're going to use what's called the interp function. So that's saying that you're going to tell me a set of points, and then we'll draw, and the leap is going to draw a straight line between those points. And so when you write interp, it populates this time series wizard that's trying to help you input these values. But we don't actually need this because we're going to do a bit of a calculation as well. So we're going to hit cancel, and we're going to type our first year, 2030. Then we're going to do a comma, and we are going to input our fuel economy value, 0.12, and we are going to say multiplied by 0.9. So that's saying a 10% reduction in our fuel economy, a 10% improvement in our fuel economy. So it's 10% less fuel consumed per vehicle kilometre travelled. Then we're going to input our next year, 2040. And then we're going to put in our fuel economy value again, 0.12. And then this time we're going to times it by 0.8. Finally, we're going to put in our final year, that's 2050, comma, 0.12, that's our fuel economy value, multiplied by 0.7. Hit close brackets and tab, and you can now see that gradual reduction over time in that energy intensity. So the vehicle is consuming less energy for every vehicle kilometre travelled. And that's a measure modelled now. That's as simple as it is. Obviously, the data you input and the assumptions that you make are the complicated bit. That's where the work is done. But that is how simple it is to model a measure within LEAP. So now go to the top where it says scenario and where it says fuel econ currently. We're going to click there, and then instead we're going to click on freight shift. We're going to model a slightly different measure this time. So instead of that intensity measure, we're now going to model a shift measure. And this is only going to be for the freight sector. Previously, we just did a fuel economy measure for passenger road cars. That was just for simplicity. We're now going to do a freight shift measure. So we're going to click on freight. And here you can see that at the moment we have a split of 80% of freight vehicle kilometre travelled are delivered on the road, whereas only 20% are delivered on rail. We want to increase the proportion of rail and decrease the proportion of road. So in order to do this, we're going to model a very simple measure. So we're going to click where it says 80, and we are going to write another interpolate function. So we're going to write interp, open brackets, a wizard is going to pop up again, and this time we can use the wizard. So what we're going to do is we're going to hit tab and tab again, and we're going to input our first year. So the assumptions under this measure are going to be that in 2030, we actually, rather than 80% of vehicle kilometres being by freight being travelled on the road, we want it to be 60%. So we're going to write 2030 and then 60. Then in 2040, we want the value to be 50%. Then in 2050, we want the value to be 40%. Once you've typed that value, you hit finish, and there you can see that it's populated this function with those three values for 2030, 2040, and 2050. So now you hit tab, and you can see the assumption has changed. What you can see also is because we have this remainder function in for rail, it's calculated the value for rail automatically every time. So rather than having to input the calculation for both modes, because we've used that remainder function, it's saved us the step. Okay, so now we have these two measures modeled. We have the fuel economy measure and we have the modal shift measure in freight, that freight modal shift. However, they are currently being modeled independently of each other. And the reason we do this is because sometimes measures will actually interact with each other. And the reduction in vehicle kilometers in one area might then affect a fuel economy value that you'd also then model on top of that. So in order to avoid double counting or any time that measures might be erasing the impact of each other, we need to model them independently as modeling the effects of them. So any modal shift measures, we model those all together. And then any energy intensity measures, we model those together. So we ensure that all of those measures that have the same effect are modeled together, and then we can aggregate them to ensure that no double counting and no contradictory effects are being present. So what that means is we're going to go up to scenarios, click scenarios, and we are actually going to add another scenario. That's going to be an aggregated scenario. So we're going to right-click baseline again, hit add, and we are going to call this scenario aggregate mitigation. Hit OK. That scenario has appeared. And now on the right-hand side, you can see that there's this box that says inheritance, and it says additional scenarios based on the baseline. So we're going to go to the right-hand side of this box where there's a plus arrow, and we're going to click it. And so now you can see these other two measure scenarios that we've already created. So what we're going to do is we're going to add these, because what we're saying is we would like to create a scenario that aggregates all of the other measure scenarios we've built under one, so we can see all of the effects together and understand the way in which they interact with each other. So what we're going to do is we're going to add freight shift, and then we're going to add again fuel econ. And now we're going to close the scenarios wizard. And so now we have this fourth scenario present, is aggregate mitigation scenario. And we don't actually need to do anything. We don't need to model any impacts under there because we've already inputted those assumptions under the specific scenarios. So what we can now do is navigate to the results tab to start to see some emissions reductions. So we head over to results, click that. Leap's going to think for a small moment and then start to produce some results. And so what you can see on screen here is an output of 100 of the emissions associated with this energy demand, and then also the emissions reduced. But what you might see on screen will be something slightly different. What you might see on screen would be something more like this. So I'm just going to navigate back to the view that you might see. So this is probably what you'll see on screen. So the baseline transport energy demand in million gigajoules, which is a very useful output and something we can use in and of itself. But we want to change this view to what I could just see. So what we're going to do is we are first going to go up to the top and change the scenario we're viewing. So where it says scenario baseline, we're going to change this to aggregate mitigation. Aggregate mitigation. I clicked on the wrong one. And now we're viewing the aggregate mitigation scenario. So you could see there was a change there in what we're seeing on screen. We're then going to go down to the next box where it says no comparison currently. We're going to click that. And where it says avoided versus, we're going to move to that selection. We're then going to move to the next part where it says scenario. And we are going to select the baseline. So what we're doing here is we are looking at what is avoided, consumption that is avoided in the aggregate mitigation scenario relative to the baseline. So avoided versus the baseline. So we're going to click baseline. And here you can see that red bar is the energy consumed in the transport sector. And then that white bar on top of that is the avoided energy consumption because of the measures we've implemented. This is already a useful output. Well, we want to go one step further. We want to see the emissions associated with this. So where it says at the top of the graph here, energy demand final units, we're going to click that. And where it says environment in the drop down, we're going to navigate to that option. And then we're going to go to the third option on our screen, which is 100-year GWP, global warming potential, direct at point of emissions. So this is just telling us which global warming potentials, so what is the climate forcing effect of the greenhouse gases that it's going to use to build its assumptions. And we want the 100-year global warming potentials to be used for this assumption. So we're going to select 100-year GWP direct at point of emissions. And now you can see there's not much of a change in the graph because energy demand and emissions are obviously directly correlated. But what we can now see is our output. We can see exactly what emissions have been avoided with the measures we've implemented relative to the baseline. This is for the aggregate. This is for both of the measures we've modeled together. But what we can do is we can also look at individual measures. So if we go up to the top again, where we selected our scenario, and rather than aggregate mitigation, we click on that drop down again, and we'll navigate to freight shift. And you can see that those white bars have reduced, so there's a smaller effect because this is only one of those measures that are in the aggregate scenario, and we can see the impact of that measure. Now we can navigate to that box again, and instead of freight shift, we're going to select fuel econ. And now you can see that fuel econ relative to our freight shift measure has a much smaller impact. but together you get that combined effect we could see in the aggregate scenario. So this can also be viewed as a table. So if we navigate back up to our aggregate mitigation scenario to see the combined effect, and at the top of this view here, we can see that it says chart, table, and split. So we go to table, and now we can see across the total time series where our emissions are being reduced. This can also be split out as well. So we can start to break down exactly where our energy is consumed and exactly where our emissions are reduced by showing different levels as well. So if we wanted to, we could increase the number of levels visible, and we can start to see the relative emissions in each of our different areas. The more levels we add, the more details it shows. But it's a way of understanding where is our energy being consumed, where are our emissions coming from, and then you can change the views as you need in order to see more specificity about where those results are coming from. So now we can see as much information as we want to see. We can see our relative energy consumption and the relative emissions, and you can start to see why, for instance, you can see that the emissions associated with our rail are very, very low, whereas the emissions associated with our freight, for instance, are very, very high. So obviously moving some of that freight to a relatively lower proportional energy intensity for rail means that we're going to save some emissions, and that's what we're seeing here. We can also navigate back to the chart and see these as a stacked bar chart where you can see the relative consumption based on each of these modes. So these are the kind of outputs we can see from LEAP, and this we can also export as a bar chart, as any kind of other chart that you would like to, a pie chart, whatever, and then also as a table if we want to use that. And these are really useful for communicating with policymakers, for communicating with colleagues, to start to see the relative impact of different measures, and then also the relative impact of different sectors of your transport sector, different subsectors. I just wanted to jump back in here to highlight a view that I think is important when we're thinking about implementing mitigation measures and achieving emissions reductions. So on the left-hand side here, we can see our branch structure that we created of our tree, and we can actually use this branch structure to navigate around the views that we can see in the results window. So what I mean by this is if I click on passenger, LEAP filters the view and just shows the emissions associated with the passenger travel, and then the avoided emissions associated with measures implemented in this category. So we know that this is the fuel economy measure in the passenger road car subsector, and we can see exactly the emissions reductions associated with that measure very, very clearly. I can do the same if I go to freight. I can see the emissions that are avoided in the freight sector because of our freight modal shift measure. This is really useful because if you can imagine having not just passenger freight for road and rail, but also for waterborne, civil aviation, several different vehicle types for road, etc., you could see that you would want to understand where the emissions reductions are taking place, where the greatest impact is going to be felt. And through this view, you can start to understand this. You can break it down measure by measure, subsector by subsector, mode by mode, vehicle type by vehicle type, and you can see where those emissions reductions are the greatest. And that can help inform any decision-making processes around prioritizing measures, understanding where investment should go, etc. So I just wanted to take this moment to highlight a very important function that LEAP can provide in the decision-making process, and I think that can be very useful for those listening. So hopefully this has been a useful introduction. We've built a very basic model here, but it takes some sophistication and it takes some thinking in order to build the structure. But it shows how basic it is in order to start to get results out of a model like this and how quickly it can be put together and you can start to see those results. So hopefully this has been a useful introduction to your journey through LEAP. As I said at the start, there are many more resources available through the Stockholm Environment Institute's website. And if you have any more questions for us, please don't hesitate to get in touch. But thank you for listening, and I really hope your journey with LEAP goes well. Thank you and goodbye.